the recording. All right, so actually maybe before we're starting, so I was also planning to give you a little bit time at the end of class to discuss the next assignment with your group members. So probably again like 15, 20 minutes or so, right? Or perhaps even a little bit more, because I think we will be relatively quick today going over the materials. So, so the regression stuff that I wanted to show you today is basically edited to the previous file, right? So that we were working with last week. Well, let me just so move all the way down to the multiple regression parts, right? Here we go. Alrighty. So I'm relatively, so just as a quick additional comment, I'm relatively brief here with my comments on the regression diagnostics, so whether that's problematic or not, or that looks good or not. So it's not, basically don't use it as a guideline for your assignments. So I still want you to be very detailed when I ask you something like check the, so whether that the assumptions have been met, etc., etc. So I want you to be very, very thorough when you do that in your assignment. So don't think that what I have in the tutorials is enough. So the tutorials are mostly so to show you a little bit our code, and then they're discussing certain things that we don't have time to address in the lecture in a little bit more detail sometimes. But they're not a template for doing your assignment. So often I expect you to be more detailed. And it's still, so also from assignments 5 and 6, so some groups are still very, very brief. So, or stay on the surface when they're asked to explain something. So I really want you to demonstrate that you know what you're doing. So if you say something like this indicates a plot indicates non-linearity, so then I want to know why. So what is it, what specific feature of the plot makes you think that this is the case, right? So it's not only stating it. I really want you to explain it and to highlight the features that that lead you to your conclusions. Right. So I've also, I mean, I tend to be generous with assigning points, even if it's like not quite as thorough as I would hope. But so moving forward, please, right? So so rather write too much than too little. Okay. So then let's get started. So multiple regression, right? So multiple regression, we discussed that in class last week, just a natural extension of simple regression. So we are adding more predictors to our model, hoping that we can improve our prediction so that we can explain more variance in our outcome variable, which is in many cases true, right? So chances are that I am adding a predictor, right? I can only improve my prediction, so it cannot get worse. So, and for today, we will use so the album sales example again, and we will add 2 predictors. So the first predictor is, so in addition to what we used for the simple regression, right, that was the amount of money or the budget that was spent on advertising, so the album. And now we are also including so another predictor, airplay, so how often the album is played on the radio, and so also the attractiveness of the band, right? So that's this the sample data set that we're working with. Okay, so you can see here, right? So we have as last time, we have the advertisement budget, we have the sales numbers. Then the airplane variables is the first additional predictor, and the attractiveness, that's a second additional predictor. And so we can see that it's a rating on a scale from 1 to 10. And for the purpose of an analysis, we can assume, let's assume it's an interval scale. Again, so that is not always clear if I don't say anything else. Also for the example data sets, you can assume that it has interval scale level, right? So you do not need to assume that's only ordinal scale level. So let's also for this example, right? So we just believe the authors, so that published the data set, that this rating is indeed an interval scale, even though it might be doubtful, right? So I mean, but we don't know how the data was actually measured. Okay. So as I said, so attractiveness rating, so from 1 to 10, and then the airplay is just a number of times. So that is obviously discrete, but a numeric variable and a ratio level scale, actually, even. Okay, so and then our model, right? So would look like that. So our sales numbers is the intercept, right? So we still have, and then so we have B1, so our first regression coefficients times the number of advertisement, so times the money spent on advertising, B2 second regression rate times the number of airplay, and B3, so the third regression coefficients times the attractiveness scores. And then also I added that I didn't write, so just as an additional comment, so please always keep in mind that this is basically a sales head value here. So that is our expected value for the sales numbers for this particular predictor combination, right? So it's always, so we first, for a given combination, so here where we have multiple predictors, right, for a given combination of predictor values, so we are predicting the basically the mean, right? So the expected value of our conditional distribution. So that this should be a sales head if you want to be super precise. All right, so the formula is very similar. So how we input that into R, right? So the general syntax is the same, right? So we assign that object that is created by the function call lm a certain name, right? So I call that album.mr for multiple regression here. And then on the left side of the tilde operator, we have our outcome variable, and then on the right side, we have our predictors here. And then we are specifying our data set, and then what we want to do is see NAs in our data sets, so the missing value. All right, and then we can call the summary function, everything as usual. So we get our formula here, we get our, so the residual statistic, right? So the minimum, maximum, or median, and the first and third quartile, all looks pretty good, right? So it's nice and symmetric, so nothing unusual here. And then our coefficients are just a larger matrix now. So instead of having only intercept and so the slope for advertisement, we have the coefficients and all the statistics for our other two predictors, right? And so, right, then there's this reminder. So the estimate here, so the first column, that is actually our coefficient, right? So that is our estimate, the point estimate of the true coefficient in the population. So of our true intercept, of the slope for advertisement, so that is basically the slope parameter for airplay, and that is the slope parameter for attractiveness. And keep in mind, so if you want to interpret that as a slope, then so it means that the other two predictors have to remain constant, right? So if you want to, right, then you could interpret basically this relationship like a simple regression between this one predictor and so the outcome variable. Okay, so we see here, right, if we would write up the regression equation, then it would be 0.084 blah blah times advertisement budget plus 3.367 times airplay plus 11.08, etc., attractiveness. This is a corresponding standard error, right? So, and that refers to our sampling distribution for our regression coefficients, right? So keep in mind, so that is only a theoretical sampling distribution, right? So if we would sample from that same population over and over and over again, so we would same sample size, we would fit our regression model. Each time we would get a different estimate for intercept, advertisement, airplane attractiveness, so different intercept and these different slope parameters, regression coefficients. So that is the standard deviation, right, of our sampling distribution. So how much would these values vary, right? So around the expected true mean, which would be the mean of our sampling distribution. Okay, so this is a corresponding t-value, right? Well, this is simply our estimate divided by the standard error. And again, so this t-value corresponds to the assumption that the true estimate, so that's the true coefficient is 0, right? That's always under the null hypothesis. So our t-value corresponds to to basically the null, so the null hypothesis idea, and that is we have no relationship between any of the predictors and our outcome variable. So none of the predictors has an influence, right? So and then also that's the intercept is there, but keep in mind, so intercept is basically just the mean difference. So we really don't, or a scaling thing, basically, where there's a scale of our outcome variable and when the predictors is the same or different. So what we are always testing is, are they different from 0? And our test statistics are the distribution of these estimates under the assumption that the null hypothesis is true. And also that's what the corresponding p-value expresses, right? So I just wanted to reiterate that because it was like, sometimes I'm not 100% precise in my language as well. So that's why it's important to keep it in mind. So the p-value refers to the probability to get an estimate that extreme, right? So for our, let's say for our slope, right, for advertisement, if the null hypothesis were true, yeah, it's the probability of the data, in this case the data is our estimate, given the null hypothesis. It does not tell us how likely the null hypothesis is given the data, right? This is about something completely different. So it tells us how likely is that estimate under the null hypothesis. And so that is what we are making our decision, what our decision is based on. If that is a very, very rare result under the null hypothesis, then we're basically, we find that enough evidence to reject the null hypothesis. And that is also one, right? So because of that logic, so that is one reason why so the significance tests have been criticized, because there's not really a good alternative. So all we are doing is we're rejecting some null hypothesis, or we're rejecting that the idea that the right, so that the coefficients are 0, but we don't come up with any good alternative hypothesis, right? So and all we can say is that, well, under the assumption that it's 0, this would be a very unlikely result. Yeah, so keep that in mind, very important, right? It's always a probability to get an estimate that extreme or more extreme, and that extreme or less extreme, under the assumption that the null hypothesis is true. Okay. So, and then, okay, the significance is all the same, right? So what we see here is our residual standard error, which is, so, I mean, I don't go back up, but so how you can compare that later yourself. So the residual standard error is actually smaller than for the simple regression model, which is not surprising, right? So because we included additional predictors, and then our multiple R squared, so it's very, very important, right? So look at the adjusted multiple R squared. That's also something that so many of you did not do when I asked you in one of the previous assignments to come up with an effect size measure. So keep in mind that we want to know what the effect size is in our, we want an estimate for the population. So that's why we usually want to work with the adjusted R squared, right? Not with our sample R squared. We want to work with the estimated population R squared. So how much is explained in the population. So those two values are here very small, very similar, so which is good. So the difference is very small. So it's like 66% is about twice as much as we explained in so with our simple regression model, right, where we had only advertisement budget. And so this is a corresponding F statistic, so which has 3 model degrees of freedom and 196 residual degrees of freedom. So which are, so we are losing residual degrees of freedom by excluding more parameters in our model. And then the corresponding p-value is close to 0. So it's definitely better than a baseline model. So that's obviously implicit test here in the F statistic, right? So we will talk about it in a second when we're actually comparing the so this model to the simple regression model. So this F statistic here, if we don't specify anything else, if we just run regular regression, it basically just always tests against C. It's a null model or the intercept only model. All right. So we have talked about it already. So our intercept in this case cannot be interpreted in a meaningful way as so, I mean, even less so than for our simple regression model where it was perhaps, right, so it was not within the X range, it was in the X range, so the range of our predictor variable for simple regression, but so it was close to it. So we had certain cases that are close to 0. That means the prediction was more unreliable, but so it wouldn't have been a horrible mistake to interpret that. But here, so it doesn't make sense at all because attractiveness cannot be smaller than lower than 1, right? So 1 is the lowest value. Okay. So, and we also noticed that if we compare our regression coefficient for advertisements to the previous model, that we see that it has changed, right? So we so in the previous model it was I have to look it up. I don't know anymore. I can't remember, so I have to go all the way up here to our model. Sorry, summary function here. All right, so here it was actually 0.01, right? So and now it is 0.08. So it's 8 times as large as it used to be. So interesting, right? So that means for each right £1,000 that we invest in advertising, the number of albums that we sell increases by 0.08 times 1,000, so 80 albums, if you hold airplay and attractiveness constant. So I say here it's smaller, but actually it's not small. I have to check again. Why do I say it's smaller? It's 0.01 here, and then it's 0.08. Just have to check whether I said anything that. Oh, yeah. I also I can't. Apparently, I can't do any math. Wait a second. So we have, yeah, of course, it's 0.09 here, not 0.01. I don't know. Wait a second. What makes me think? Don't know where I saw a 1. So it's 0.09 here. So, and then it's 0.08 in our new regression models, and it's actually smaller. So, and so for, and then of course, so as if you have for airplay, we have a value of, sorry. So for airplay, or the estimate for our regression coefficient is 3.36, and for attractiveness 11.08. So that means, again, right, so interpretation is airplay increases by 1 unit. So that means if the album is played 1 more time on the radio for each time the album is played on the radio, so we are selling 3,370 more albums. Yeah, not really. It's, yeah, roughly if you round it up. And then for attractiveness is so basically for each point, so that the band is rated more attractive. So the 11,000 albums more are sold, right? If you hold advertisement and airplay constant. And then, of course, all the coefficients are significantly different from 0. That's what we would conclude here for this exam. All right. So what is important to keep in mind, so we were talking about that last week, is that the, so how large the coefficients are themselves doesn't tell us anything about how important they are. So basically how much variance they're explaining in our outcome variable. So in order to get a better idea, so what people occasionally do is they standardize those regression coefficients, and it's basically just doing a Z transformation on all predictors and the outcome variable. So which means you bring them on the same scale, right? So they all have a mean of 0 and a standard deviation of 1 then. So that means you express, so then the regression coefficients express standard deviations, right? So if you increase the predictor by 1 standard deviation, so how many standard deviations does the outcome variable increase or decrease, depending whether it's positive or negative. So and if we do that in R, so we need so a package that is called lm.beta. Unfortunately, so it used to be, if I remember that correctly, so it used to be part of the base package, but so it doesn't work anymore. So really need this extra package. So if you find a way to do it with a standard R base package, so let me know. So I thought that the beta weights were included in R, but it didn't work for me anymore. So I really had to install this extra package. If we wanted to get these standardized coefficients, so we would call this function with with our estimated model, and then we get our standardized regression coefficients. And then no surprise, right? The intercept is 0 because so all our variables are on the same scale now. So I have a mean of 0. And since so the predicted outcome value for the mean of each predictor is always the mean of the outcome, it has to be 0 as well, right? So that's why the intercept is 0. Okay. So we also know, right? So keep that in mind that so the regression line always goes through the point mean x, mean y, and that is also true for multiple regression, right? So it always goes through the point mean x1, mean x2, mean x3, mean y. Yeah, if you have 3 predictors, so it's like a 4-dimensional space. And then it's not a regression line, it's not a regression line anymore, it's of course a hyperplane, right? So it's a little bit hard to, using your imagination now as a spatial thing to think about how that would look like. So because we can only think in 3 dimensions. So it's an abstract idea. Okay. So and now what we see here is that so our regression coefficients, or the standardized regression coefficients for advertisement and airplay are actually quite similar, right? So they're all so they're both 0.5, whereas the one for attractiveness is much lower, right? And that is basically almost the opposite of what we saw before, where the attractiveness coefficient was the highest one, and then airplay and especially advertisement budget was much lower. So which was most likely, so not most likely, but definitely related to the scale for advertisement. So, and from that, we can conclude that actually advertisement and airplay are more important than attractiveness. So that to explain more variance or more unique variance in our outcome variable and the sales numbers than attractiveness. So the attractiveness of the band doesn't add much more explanatory power, right? So to our model compared to the other two. All right, so this is just a basically to repeat that concept of so how the standardization of the standardizing the coefficients changes the interpretation of the regression coefficients. Okay, so all right. So now we come to the most important point of so today's class. I would say was the newest point, so that we haven't talked about before. So what we typically want to do when we are often want to do when we are running a regression model is we want to compare multiple models against each other. So, for example, here in this case, we noticed that when we were including only one predictor, so the R squared, so our explained variance was not very large. And we were hoping that we can maybe explain a little bit more of so what drives or what determines the number of album sales. So we included additional predictors in our model. And now what we're interested in is not only is this new model significantly different from the null model, so basically if we wouldn't include any predictors. So what we want to know is it significantly better than the model that has only one predictor, right? And so because, I mean, we can look at the R squared and can say, well, that is twice as large as the R squared for the simple regression model. But is that a significant, so a statistically significant increase? So is that reliable? So, or is it something that is a probable result, even if the two, basically, if they came from the same underlying population, so that can be basically where airplay and attractiveness actually don't play a role. And it is not enough to show that airplay and attractiveness themselves are significant, right? So that is not equivalent to showing that the model as a whole does better than the simple regression models that count only advertisements as a predictor included. So what we could do and what would be equivalent is, so if we, so let's assume we would include only one additional predictor at a time, right? So if we would say, well, so we started with a model that included only advertisement as predictor, and now we wanted to test whether a model with airplay as additional predictor does better. So if we then compare the model with one predictor and the model with two predictors, and we run an F-test to compare these two models, then the result of this F-test is equivalent to the test of the regression coefficient in our two predictor model, right? So these are the F-tests for the model improvement and the T-test for the second predictor. That is equivalent, right? If we would do that, but if we have more than one, so then it does no longer work. And that is actually a logic. So that's something that we will discuss that when we are actually doing mixed linear models, because so for mixed linear models, it is the only way, so or the standard way at the moment, the gold standard, to determine whether your predictors are significant, so or make a significant contribution to the model, because it's really hard for these models to determine the degrees of freedom. But that we will talk about in either next week or in 2 weeks. Okay, so alrighty, and in R, in order to run this model comparison in R, and I already said is an F-test, right? So we're using a function that is called ANOVA. So this ANOVA function we will use quite a lot, and it will be quite important for you if you work with your own data, right? So and it is ANOVA is a model comparison. It compares two models. And so one model is called a restricted model, and the other model is called a full model. So you always have, when you're using ANOVA, you always have a model that has fewer predictors, and second model that has more predictors. And what you want to test is whether the full model that has more predictors does a better job. So whether the R squared is significantly larger, right? So for the second model than for the first model, right? For the restricted model compared to the full model. And then again, restricted and full are relative terms, right? So if you run like a regular regression analysis, and your restricted model is the intercept only model. So it's a model with zero, that's implicit basically, right? It's a model that has zero predictors. And here, when you're using so the ANOVA functions, and you could, for example, test a model that has 2 predictors against a model that has 5 predictors, or you can test a model that has 20 predictors against a model that has 40 predictors. I mean, how meaningful it is, I don't know, but you can do that, right? So it's what's full, what's restricted is all relative. So the restricted model has fewer predictors, the full model has more predictors. So that's the decisive point here. Okay. So it's very easy, right? So you just type ANOVA, and then as arguments, you pass your 2 models, and you always start with a restricted model, right? So the restricted model is always your first argument, and then the full model is your second argument, right? So in this case here, it's our simple regression models. It has only advertisement as predictor, and this our model that has its 3 predictors here. And here, so you get your output, right? So it first repeats for you what the model equations were for your 2 models. So just to double check, that's correct, right? And you can see here, that's what we did. And then you get 2 lines of output. So this is basically just a summary of your, so for certain statistics for your restricted model. And then, so this more complete line of output here is for the model comparison. Right, so that is irrelevant information here. And what we can see, so the first is the residual degrees of freedom, which corresponds to what we saw in our previous model already, right? So the residual degrees of freedom, 196, because we're basically losing 2 degrees of freedom by including 2 more predictors. And so you also see that we have a degrees of freedom here in our second row, which is the second row is for the model comparison. And that is, so this 2 here is our enumerator degree. So these are the enumerator degrees of freedom. And it's just a difference in the degrees of freedom between our restricted model and the full model, right? Which in this case are 2. So we have 2 more, right? We have 2 more predictors. So we are losing 2 degrees of freedom. So the difference in degrees of freedom is 2 here between the restricted model and the full model. So that's why you can, by the way, never use ANOVA to compare 2 models that have the same number of predictors, right? Then you have 0 degrees of freedom, so that doesn't work, cannot be estimated. So here you have, so in this line, right? So you have your residual sum of squares. So basically that is the squared deviations of all data points, right? So real data points from your estimated regression function, so your estimated hyperplane. And so this is a pretty large number, not surprising, we have many data points here. And so this is a number for your complete model, right? And you can already see that this number here is twice as high, so you have much larger residual variability for your restricted model compared to your full model. And so here, so under sum of squares, you simply see the difference, right? So the difference in sum of squares between the unexplained variance variability in the first model and the unexplained variability in the second model. And so, and this is your corresponding F statistic here, right? You can see that's pretty large, and the corresponding p-value is small, right? It's close to 0, so not surprisingly. Okay. So,
Professor?
Yeah.
So when I type in the ANOVA code, I keep getting an error, and I can only do an overall analysis of variance table.
So can you, I don't know what that means. What is the error message?
It just says that the object's not found for album sales, simple album sales, like however I have the variables.
Right, so you have to you have to run the simple regression model again. So you have to do this here. So you have to run your model, and then, right, you need a simple regression model. So you have to have album sales simple, and otherwise, if it's not in your environment, you cannot compare the two models.
Right. Okay, I got it. Thank you.
Okay. So, all right. Okay. Okay, and then as I said, so that is very brief overview. If you want to look just at this a plot of your multiple bivariate relationships, so then you can do that with a pairs command in R. So what probably is the most interesting one is how sales, so basically how the relationship of all predictors looks like for so with the outcome variable, right? So which you can see either here or here, depending on how you want to define it. And then we already, right, that's basically the same diagram that we looked at when we did the simple regression analysis, and so we noticed that. So we have what is not unexpected. So we have basically no values here for large advertisement budget. So almost all sales numbers are high. So it's basically there are no cases where company spends a lot of money on advertisement, but then sells only a few albums. But so in the for lower investment, so we have quite a lot of variability, right? So that's why I said in my tutorial last week, maybe, so there's another variable that we have to take into account, right? So that like something like popularity of the band or whatever. So often it's played on the radio, which explains why even though the investment or the advertising of the album is low, the sales numbers can be high, right? So maybe let's see this influence of the third variables. So that is just the same. And so this looks pretty good here. So there's no reason to think that there's anything odd. And also, I also noticed something which I did not anticipate. So I was a bit surprised that so this idea of like linearity and the assumption of linearity that was not 100% or not as clear as I thought. So so from reading your assignments. So that's why I wanted to restate the idea behind the linearity assumption is that so it's simply that if you have a nonlinear relationship between your predictor and the outcome in regression, then your outcome, so basically the estimated regression function will not be appropriate. Yeah, so that means that you have the fact, so and also the model, so basically so the assumptions that have to be met, like so your homoscedasticity and etc., that will be violated. So the normally distributed error terms, etc., etc. Well, that happens. So always think about good examples as inverted U-shaped relationship between a predictor and outcome variable, right? So it looks like an inverted U. So that you have like low outcome values for both, for low and high predictor values. Right, that's often the case for stress, right? So too little is not good, too much is not good, right? And then you have this sweet spot. So actually, it's also for activation levels, etc., etc. It's often also in transmitter, as a neurotransmitter action, right? So if you, for example, for dopamine, you also have this inverted U-shaped relationship, right? So too little is not good, too much is also not good. So that we see that quite a lot. So and if that happens, so then so the assumptions for linear regression are not met. However, if we simply have no relationship between outcome and between predictor and outcome, that is fine. So that does not violate any assumptions. That means if it's just like a random cloud, a random clutter of points, and there's no obvious trend, and this is fine. So that is not, does not mean that we cannot estimate a regression model. So they might simply be a weak relationship, right? So the important thing is it's not a nonlinear relationship, right? So that is what we are tracking when we are looking at um, at our scatter plots. So we are not checking, is there a strong relationship, and that is the assumption for running this regression model. We are checking, is there any evidence for a nonlinear relationship which would make our model invalid? That's what we want to rule out. So that's why we do this linearity check. If there's simply no relationship, that's fine, right? So if it's a zero relationship, it's okay as long as it's not nonlinear. Yeah, I hope that is a bit clearer now. Okay, so that looks okay. And then this looks a little bit funny here because so attractiveness has only this 9 possible values. So we have very few. You can already see, right, that attractiveness is skewed here. So we have only very few bands that are rated low on the attractiveness scale. So most bands are rated very highly in terms of attractiveness. So that's why that most likely because of skew in our, so one of the predictors is a bit skewed. So we see that a little bit funny looking pattern here. And then the fact, right, so that you have these columns here that is simply driven by the fact that we, right, in comparison to these clouds here or the scatter is because a predictor can only take on 9 different values, right? So it cannot be in between. All right, so but apart from that, it all looks okay. So there's nothing that looks like a nonlinear relationship, right? So there's nothing that looks like that or that or something like a cubic thing, right? So here for that's our residual plot, right? So it plots the fitted values. So basically our y hat, so it's predicted values against the residuals. And so here it's important, right, so that they're evenly spread around our zero line here, this horizontal zero line. It looks pretty good, right? So this red line is the actual mean for each fitted value here. And there's nothing to be super concerned about. Yeah? So it looks pretty good. So there are a few unusual values that are flagged here, but doesn't look super concerning. Same as for the normality assumptions, so that the residuals are normally distributed. We see like a little bit of deviation here. So this is an outlier, right, out of 169. So basically that is so that is basically something that we already see here, right? So the residual is just very large. So whereas here for 164, right, it's very small, and then 47, it's also very small, but it's still, right, so the scale overall here of our, these are the standardized residuals, right? So scale overall, it's within this -3, +3 range. So with the number of data points we have, that's fine, right? So it's not like, it's nothing that I would get super concerned about. It's not like we have a 10 here and then a -10 or something like that. So that looks pretty good, right? So there's a little bit deviation here, so that the actual residuals are here a bit more extreme in the lower end than they should be here. The same, right? So they're a little bit more extreme than they should be at both ends, but nothing that is outrageous. Okay. So scale location plot, also just a reminder, it's very similar to what we see here. The main difference is that if there's evidence for heteroscedasticity, right, so that's what we're checking, the most important thing that we're checking here, also nonlinearity, right? So if we would, for example, if we had a nonlinear relationship, so then we could see something like inverted U, right, here, or whatever, something nonlinear, right? So which we don't see here. So the scale location plot is very similar. The only thing so that makes it a bit easier to detect heteroscedasticity, because if there's heteroscedasticity, we would see a non-horizontal red line here, right? So that would be a trend, just easier to look at, or easier to identify. And so we can see that those are pretty good. So there's no reason for concern. And let's see residuals versus leverage plot again. So right, in order that is to determine whether we have any influential outliers in our data set. Just a reminder, right? So we're not that much concerned about outliers per se, but about those that are influential, that have a big impact on the regression model, on the coefficients. And so those are data points that have large leverage and large residuals. So, and that looks all pretty good here, right? So the ones with the largest leverage have actually the smallest residuals. So small residuals, that means they're they align very well with the regression model. So, and then our one at 69, right, so which has a large residual, has small leverage. So that's why it's not that much of a problem. And then one at 64 has sort of, yeah, moderate leverage. So definitely worth looking at here. Also the one, right? So 169 and 164. These are definitely worth checking for validity and to get a better idea what's going on. But it's nothing that concerns us too much. And so then if we want to be like really thorough, we can use this influence measures function, which flags many more data points. It's just if we really want to make sure that everything's okay. And so it has all the different statistics that basically flag potentially influential observations, right? So the Cook-Spees and or DF beta, et cetera, and the leverage values. So we will talk a bit more about some of them tomorrow. And then wherever there's a star, right? So that is a case that has in any of those statistics a slightly unusual value, right? So, and if we want to be like really thorough, we could check all these flagged cases here, just to make sure that there's everything correct with them and that they are right, so that that there was no error with the data entry or something, right? So else that would justify an exclusion of the data points. All right, so one thing that we didn't need to do in simple linear regression that's very important in multiple regression is to check for multicollinearity. So we will talk about the theoretical underpinnings in more detail tomorrow in class. So here I just wanted to include it for you to know how you can run the diagnostics in R. So just very quickly, so what can constitute a problem for estimating the valid regression weights is if our predictors are very highly correlated with each other. So let's assume that I have, so that, for example, advertisement and airplay would be like correlated 0.9, right? So then it more or less would mean that they're redundant. So first of all, so then it's in the first place not necessary to include both of them in our model because they basically contain the same information, right? If they're so highly correlated, and they cause the additional problem that so they make the estimation of the regression rates extremely unstable, right? So that's basically, it makes a standard error for the regression weights super large, so it inflates the standard errors. So it has absolutely no impact on your R squared and the corresponding F statistic. So it does not affect your model as a whole, how well your model performs as a whole, but it makes the estimates, so basically what your exact regression coefficients for these highly correlated predictors are super unstable. And so because the standard error, right? I mean, right? So what you can think about it, it's almost intuitive, right? So if you have these highly correlated predictors, then if you go from sample to sample, so then in one case, so one might be more influential. In the other case, the other one might be more influential in terms of, right? So that it goes basically back and forth depending on what your particular sample looks like. That's why you have this huge fluctuation in their range, right, of potential values if you sample different samples from your population. So you basically don't know exactly what the beta weight is. You know what your R squared is, but you don't know the exact beta weights. So, and then so what we normally do is we just exclude one of the two predictors from our model, right? So they're not adding any if they're, again, if they contain so much overlap in their information, then typically they don't add anything to the model anyway. There are some interesting exceptions, so which are called suppressor effects. I have an example for that in the tutorial that I posted earlier. So that's this fashion model data set. I will actually upload the data to R as well, because to Blackboard, so that maybe you can run that yourself and make that an extra document. It's because it happens not that infrequently in real life, and it's also important to understand, but getting ahead of myself. So here we just want to make sure that we don't have too much correlation between our predictors. Okay. So here, so always a good starting point is to look at the bivariate correlations between the predictors. And so for advertisement, let's just look for advertisement, right? So it correlates with airplane 0.1 with attractiveness 0.08. So that's completely unproblematic. And then we have airplay and attractiveness, it's 0.18. So nothing that really concerns us here. Absolutely nothing, right? So these are all low. So it's not that easy, but usually, as long as the bivariate correlation coefficients don't get close to 0.8, it's usually fine. Not always, usually, not always. Sometimes even moderate intercorrelation can have the weirdest effects, but normally it should be okay. So in addition to these bivariate correlation checks, right, to see that how highly they are correlated with each other, so it's only important, right? So I have, just for, of course I was lazy, I included sales or outcome here. That is not relevant, right? So we are just looking at the intercorrelation of the predictors. Yeah, so sales, we don't care. Oh, I mean, that is the outcome. We want them to correlate very highly with the outcome, but not with each other. All right, so the VIF criterion is one that is frequently used to quantify the amount of multicollinearity between your predictors. And it basically estimates how much the variance of your coefficients or your error variance is inflated because of the dependency between the different predictors, right? So that basically says how much is it, so by what factor it's multiplied, because there is, as opposed to if you would exclude this highly correlated other predictor from your model, or these other predictors, right? It can be more than one. So how much would, by how much would or how many times would your standard error estimate be reduced for this particular predictor? So that's what the VIF tests. And here, as you can see, they're all close to 1. So 1 is the minimum. So that means there is really, really no evidence for multicollinearity here, any issues, right? So if it would be 10, 8, so that would be concerning, right? So, but, so this looks all pretty good. And then there's, as usual, right? So there's a disagreement on what a good cutoff value is. So I usually get a little bit concerned if it gets close to 3. At least I think a little bit more deeply about my model then, and I check what happens if I exclude one of the two predictors, right? And how that changes the parameters, et cetera, et cetera. But so in this case, we have absolutely no reason to be worried. And then one last point is, so despite the fact that we are not actually that much interested in multivariate outliers per se, I just wanted to show you how to calculate the Mahalanobis distance in R, because it's just something that you will come across frequently, and it's important for many other applications actually. So the Mahalanobis distance is a very important and useful metric. And therefore, I just wanted to include that here, right? So if we want to know, do we have any multivariate outliers, so outliers that are just far away from our centroid, so it's basically the mean of our multidimensional data cloud, right? How many dimensions our data cloud has depends on how many predictors we have, right? So here we have 3 predictors, so it's like 4-dimensional. And so what we need is the function Mahalanobis that comes with the R-based package and has this general syntax. So it acts always our data frame, so our data matrix. So if we have more, of course, if we have more variables in our data frame, then we need to basically select the subset that is relevant. Then center is the mean vector of our multivariate distribution, right? So this basically is so it's a mean of our linear combination, so all predictors combined. So int our outcome variable, and then covariance is the corresponding covariance matrix, right, for our distribution. And then for our example, if we want to get the Mahalanobis distance for each album, so for each case, so we just give it our, right, so the original data frame, then the so the mean of our covariance matrix, so we pull that mean, so using the function colMean, so just the means from all columns combined, and then the covariance of our 4 data vectors, right? So for 4 variables, so the variance covariance matrix. Okay, and that is the output, right? So that we're getting for each of our 100, for each of our 200 data points, for each of our 200 albums, we're getting 1 value. You can see they vary quite a lot. So we have one that's as high as 17, and then we also have others that are below 1. And so it can be shown that so the Mahalanobis distance is approximately chi-squared distributed for a sufficiently large sample size. So we have a large sample here, so that's okay. That means we can just run a test to see whether so the distance of a given data point is larger than we would expect if the data would follow by a multivariate normal distribution. And we do that, right? So we basically first we add the Mahalanobis distance to our data frame here. We just add a new column that has a distance, and then we calculate the chi-squared statistic for that. So the chi-squared statistic p-value for that distance, right, for each individual case. So degrees of freedom are 3 here. It's always a number of variables minus 1. So then lower tail is false here. And so we are checking basically which value, which case has a distance that is with a p-value smaller than 0.001, which is a pretty common metric to use. And so then we see here case 7, 138 and 181. So there's the ones that are maybe a little unusual in terms of their distance from the data cloud, right? So from the center of our big data cloud that includes all cases. And so it's important to note that this does not, so these values do not correspond, or these cases do not correspond to what were perhaps the most influential ones, right? So 169, the 164, the 1. So that means, and also important to keep in mind that the Mahalanobis distance is actually closely related to leverage. So that means how extreme are the predictor values of for our cases. But that doesn't necessarily mean that they actually have an undue influence on our regression model. So in this case, these values here, or these cases, actually seem to correspond quite well with a regression model, despite the fact that they tend to be extreme cases on the predictors, right? So they have extreme X values, they have extreme predictor values, they have maybe like a particularly high budget. And for advertising, they might be particularly attractive or particularly unattractive. They might be, right, the songs might be played either unusually frequently or or never, right? So they're for the predictors, they are at the extreme ends of their distributions, right? But that does not mean they're inconsistent with the regression model. So they have the potential to be influential, but because they don't have huge residuals, so then they're not. But it's also I included that here, so you can see that they are highlighted. All of them are highlighted here because they have relatively large leverage, right? So that corresponds to this idea that leverage and Mahalanobis distance are closely related, and that they are more extreme in terms of their predictor values than they're actually problematic for the regression. Okay. I hope that was relatively clear. So do you have any other questions, especially regarding the next assignment? Is there anything that you need to know for the assignment that you feel you haven't discussed or that's not in the tutorials? Yeah? Okay, if so, let me know. All right, so then for maybe another 15 minutes or so, I just wanted to talk a little bit about robust regression because we sort of like skipped over that last time, and I think it was quite unclear. So hopefully that will make things a little bit more understandable because I really didn't say much about the robust regression, and it is important, right? Okay, so just as a reminder, right? So I included these here as a basic terms, right? We are always concerned about our residuals, right? That's the difference between the predicted values, right? Our y-hats and the actual observed values. So how far away are they from our regression model, right? So our predicted, our actual values, so the actual outcome values compared to what we predict in our regression model. So an outlier, an regression outlier, right? So there are multiple definitions for outliers, but in a regression outlier is an observation that has a large residual, right? And then we have leverage, that's an extreme predictor value or combination of predictor values. And then we have the influential ones that are, so the observations that have make a huge impact on the estimation of the regression model, and that is usually operationalized or measured as how much would the regression model as a whole change if we removed that value from our data set and would refit the regression model. So would the parameters change a lot? And then we have Cook's distance, right? That is a measure that combines leverage and residuals of the observation. It's a measure of influence. Okay, that is just as a reminder, right, of the different terms. And in general, so you can use robust regression whenever. So whenever you would use our ordinary least squares regression, you can also use robust regression. But it's particularly important, so to use, I mean, let me recap, right? So what robust regression does, it's so basically either weighs down or eliminates the influence of like a certain number of data points in the estimation of our regression model. So that means in the worst case scenario, if we use robust regression on a data set that has no issues, right? So where there are not really influential cases or, right? So then we are just wasting good data. So we are just basically wasting power. So we are running our model on a reduced data set, or we are basically, so why would we want to do that, right? So there's no need to do that if there's no reason to believe that there's an issue. But if we think there might be, we might have influential cases. So there are like, so we might have quite a few data points that have unusually large residuals. So we might have quite a few data points with huge leverage. So then we are concerned about the impact of these data points on our regression model. So then that would be a situation where we want to do, where we want to run a robust regression model. So we want to use a robust estimation method. And then just as a reminder, so the whole idea is that so we are reducing the impact of cases that are unusual, right? Yeah. Is there a question? Yeah, so we're basically, so when we are all these robust regression methods, so either they're completely ignoring data points that are considered contaminated, right? So that have an undue influence on the regression model, that are whatever reason inconsistent with the remainder of the data sets as a data points in estimating the model. It either completely excludes these data points from the analysis, or it assigns them a smaller weight, right? So they have less influence in estimating the regression equation. So they have a reduced impact on determining what the coefficients look like. So, and the most important criterion for that are the residuals, and especially the studentized residuals. So how much would the how much do the data points deviate from the regression model if the data points themselves are not included in the analysis, right? If they are not included in the estimation of the regression model themselves. Okay. So one important, I mean, there are many packages that do robust regression in R. So one of the oldest and most popular ones is called the MAS package. So there are many. So it's actually quite a few, and especially in the past few years, so more have been added. So that is just one that we are focusing on here. But so I would encourage you to do your own research. There are actually really quite a few that you can use. And so the MAS package implements several versions of robust regression. So one that's also a very popular method is called M-estimation. And so for the M-estimation, so that was also in the slides from last week's class. So we basically use, so the idea is as follows, right? So we want to reduce the influence that these unruly cases have on the estimation of our regression function, right? So we might have cases that have like really huge studentized residuals, and we want to basically those cases that are that do not correspond to our regression model, and especially not if they are not included in the calculation of the model, right? So if they are deviating from the model that is estimated based on all other data points. So then we want to reduce how much weight those data points have when estimating the model. So estimating the coefficients, right? So estimating the regression equation. And so what M-estimators or M-estimation does, so instead of minimizing the sum of the least squares, it uses a different function, right? So not the least squares, but it does something different, right? So, and what that is, so there are different alternatives. So one is called Huber rating, right? So that is a pretty straightforward function, and it's based on how large the residuals are, right? So the weight, so the underlying idea is that so observations that have small residuals get a weight of 1, right? And then basically it's some pre-specified threshold. And then the larger the residual is, the smaller the weight that is assigned to this case, right? So that makes sense. So the maximum weight of 1 is for cases that have a small residual, so that correspond very well with the regression model. And then the more a case deviates, the smaller the residual, right? The smaller the weight. So and then, so we, as I said, so you also have bi-square weighting. That is another option. So there are several. There are more than these two, right? And so the bi-square works a little bit differently, but so the idea is similar, right? If you have a non-zero residual, it gets weighted down. So it has less of an influence on estimating the regression equation. So one quote unquote problem with this approach is that, so actually I have I think I have an updated version of that on the on Blackboard. Let me just check very quickly here. Second. Where is my? All right. So one of the issues is that we have to use so that our so well, let me, it's always hard to determine where to stop it. So we know that when we use the M estimation, so our weights depend on the residuals, right? So how much we want to weigh a case depends on the residual of this case. On the other hand, the residual depends on the coefficients, and the coefficients depend on the weights, right? So that is basically like a circular thing. So we don't know exactly where to start, right? And that's why so these M estimators are solved iteratively. Yeah. So what is often done is that you start with ordinary least regression. So you basically just estimate your model as you would do in your normal linear regression. So you just minimize the sum of squares, and then so that way you determine your residuals and you determine your regression, right? So your then you have your residuals. You can determine the weights that you want to assign these cases based on these residuals, and then in the next step, you rerun the entire analysis with your re-weighted cases, right? So, and you do that, and you start over, and you loop through that as long as until your regression coefficients converge, right? So once again, so you start with your ordinary least squares regression to obtain your coefficients. Then you calculate the residuals, right, for that solution. Then you use your weighting function to assign your cases based on their residuals a certain weight, right? So in this first run, so cases that have a huge residual that will be assigned a small weight. Cases that have residual close to 0 will be assigned a large weight, so it's close to 1 or 1. And then you rerun your regression. And then you do the same thing. And at some point, so the coefficients won't change anymore. And if that point is reached, if they will converge, right? So and at some point, there won't be any change anymore. And at that point, the algorithm stops. So that's what this iterative estimation procedure is like. Okay. So, and so here for this example, we will use a data set. It's, as I said, actually from the textbook, and it's about violent crime rates. And so what we're using here is poverty and so the parent single status, so whether they're single or married. So we use that as predictors. And so if we run so first, if we might, so you have there are more variables in the data set, but we're not focusing on those right now. And if you first run the ordinary least squares model, right? So the way we typically do that, and you get your regression statistics here, the residual statistics, and your model, right? With the estimates, intercept, poverty, singles. So that's basically the single parent is significant, poverty is not here. And you have your multiple R squared, but it's actually pretty large, and so that it seems to be a good model. However, I don't want to go into that. You already see here in your plot that you have a number of cases that are problematic, so 9, 25, 51. So there's clear evidence here for heteroscedasticity. So you see that also here 51, 9, 25, they really stick out in terms of their right, in the QQ plot here, so that's not good. And then the scale location, that's what I mean, right? So for the scale location, you have to see this clear trend here. So that also indicates heteroscedasticity. And so that is finally a plot where, Cook's D is, so where there are certain values that are exceeding these thresholds here. So you can see this is basically what R uses. It plots a line for where Cook's D is 0.5, and then another one where it's 1. So that is a very liberal threshold. It's sometimes recommended, but so 1 is definitely too liberal. So I would recommend to stick to the one that's, that we have talked about. So there you could also use the F statistic or distribution to identify so influential cases, but so we can use the one that we talked about in class. And you can see that 51, right, exceeds these boundaries here. And right, so we as I said, we focus on the upper corner here and the lower corner. And 25 is between 0.5 and 1, so it's also not great. 9 is, it's okay, right? It's not, it doesn't have too much leverage despite having a relatively large residual. But 51 and 25 is clearly problematic here. Okay. So, and if you want to see what states, so they represent, so that's Florida, Missouri, and DC. I don't know why they included DC in the data set. It's not really a state, but anyway. So, so that's why I think DC should be excluded anyway. Okay. Right, so that is our regular cutoff point here for Cooks, and you can basically you can calculate that as well for this data set, right? So all your regression diagnostics just adds a Cook's distance and then your residuals, so your standardized residuals to your original data set, right? Okay. So, and then if you want to know which cases have the actually the largest absolute residuals, so then we see that is Missouri, Florida, DC, which is still in the data set, Vermont, Montana, right, Maine, etc., etc. So these are the cases that have the largest residuals based on the ordinary least squares regression. Okay. If you want to do so the robust regression, then you use the RLM function that's included in the mass package. So, so the syntax is very similar, right? So there are a few arguments that are specific to RLM that are not included in your LM method. So we're to refer to the help function, but so you can just run the standard model here, right? I call it RR Huber here, and then you basically just call the summary. And you can see that, so if you compare that to our ordinarily squares regression, right? So we see that was 6.78 and 166 here, our coefficients, so that they are different, right? So you will also notice there are no p-values, which might be a little bit inconvenient. So you actually have to calculate them sort of by hand. We'll show you how to do that later. So if you would now, order, so the cases by the weight that, so the M estimator here assigns to them, then, right, we can do that. So if we get the, our object from our RLM, so it will have a few additional attributes. So our regression object, and one of them are the weights, right? So that have been assigned to our cases based on so this Huber weighting function. And so they can be pulled out, right? By if you just access the field W. So these are the weights, right? So if you basically call your regression object here from the robust regression, and then you pull out the variable weight or the field weight from this object, right? So it also has the residuals here. And we can order them by weight, and then we see that those states that have relatively large residuals also have so smaller weights, right? So the ones that have larger residuals have smaller weights, right? We see Missouri here has a really large residual, has only a 0.28 weight, whereas Alabama and Arkansas Arkansas, which have much smaller residuals, have like 1, right? So that's what I said earlier. So cases that have smaller residuals will be assigned a larger weight than cases that have larger residuals. And so this is just for demonstration purposes. We can also use a different method for the weighting function, not the Huber method, but what's called the bi-square weighting function. So which does more or less the same thing, just the details that are a little bit different, that again would go beyond the scope of this class. But so that just to show you, so here Missouri is downweight even more, right? So then in the Huber, by the Huber algorithm, so it basically has almost a 0 weight here. But the same goes, right? So the cases that have large residuals, be they positive or negative, have really small weights. And then the cases that have smaller residuals have larger weights. So that is the underlying idea. All right. So, so what does not change though is if you look at the outcome here, is that in both so in all 3 cases, so it's never the case that poverty is a significant predictor, right? It's always single. So no matter what you run here, it is just the coefficient for, so the regression coefficient for single that changes between the methods. So these 2 first examples used M estimation, where you're basically assigning each case a new weight. And then there are other estimation options available in RLM, and there are also other R commands for robust regression. And so one that was also in the slides is actually something that is called resistant regression, because it does not assign a lower weight to these cases that have large residuals. So that's an oversimplification, is a large residuals, right? So keep that in mind. But it basically completely excludes them from estimating the model. So the idea here is that you really estimate the model only on your clean data points. And so the method is that you're so you're minimizing the sum of the sum of squares of a subset of your original data points. So that is usually labeled K or sometimes labeled P. And so K is at least half of the number of observations in a data set. Right? So K is not smaller than 50% of your data. And then you have the option to use actually more of your data by choosing a parameter, it's called alpha. You can also specify that in R, right? You can just give it as an additional argument here to this function. Its default is 0.5. So in 0.5 means you're using roughly 50% of your data. If you would do alpha 0.75, you would use 75 roughly of your data, percent of your data. So you have basically some choice. So how much you want to use, because you, if you don't expect your data to be heavily contaminated by so invalid cases, then so you don't want to throw out half of your data, right? So you want to use more. Okay. So and the so there's actually this function or this method comes with the R base package. So and it is, the function is called LTSREG, for running the so the least trim squared regression. So what it basically does is it I mean that it's not what happens in so in reality, so because they are more efficient algorithms, but it basically, once you have determined how many data points you want to include in the estimation, then it iterates about all potential partitions of your data set, right? If you say, I want to use 50% of my data points to run this robust regression, then so what the algorithm is doing, it's basically dividing it's selecting all theory, right? All possible 50 subsets that contain like 26 data points, right? So we have here 51 cases. So it might basically divide your data and basically in all potential partitions that all include 26 data points. And then it's running an ordinary least squares regression for each of these subsets. And it tries to find the an optimized and ideal solution. And it's based on various criteria. So for example, the studentized residuals, how much your coefficients change so over the different solutions, right? So, but it's basically trying to find the ideal solution. So for the best subset, right? So where you have the basically an optimized model. So that is the underlying idea. All right. So, and the syntax is also, as I said, so these are all based on the LM function. So the syntax is very, very similar here. I didn't specify any additional arguments. As I said, so you could at least specify the alpha as an additional argument, but there are many more that you could specify. And so again, you see that so poverty is not a significant predictor, although it's getting closer here. So, and that the estimates for single have changed as well, right? So your beta weight as your regression weight is quite different from what it was before. And then you can basically use the same regression functions that or the regression related functions that are available for LM. So you can use a plot function to get some diagnostics. So you get your QQ plot, right? So you get that is a little bit so modified here based on the that it's a different method, right? So you have your index, so that it's just your case numbers, and then it plots the standardized LTS residuals, so that's at least term squares residuals. So against those index numbers, we see 9, 25, 51, right? The one that are clearly marked as problematic here as before. You have residuals versus fitted plot that also highlights the same three problematic cases. And this here is a standardized, so the standardized LTS, so residual from your LTS regression. And this is a robust distance measure. So it's basically a distance measure that is not influenced by outliers, right? So so the distances so that are calculated for the data points are basically based on this good data points only. So the model. All right. And you can see that there are a few more that are diagnosed as unruly here, right? Okay. So a specific, so what you can see here is that so we also can order the states by their residuals, right? And we see that there's actually quite a lot of overlap between the states that we have identified here, right? So it's Missouri, Florida, so they're all in here as well, and DC. And so so the object that we are creating here, so our regression object has a few additional features, right? So in the same way that the object for the M estimator had these weights that are assigned. So here we have additional field that tells us which actually were the cases that were used to estimate the model. And we see these are 1, 2, 3, 4, 6, 10, 11, 12, etc., etc. So in all others that are not included here were not used to fit the model, right? So these were considered bad ones. So these are considered good data points. Yeah, so these are the cases that were used for actually estimating the model. Okay, yeah. So then one last thing that I include here is that robust regression does not always have a problem of heteroscedasticity, for example. If you have problems with non-normal errors or like heteroscedasticity, then but we are not like super concerned about outliers or influential cases, then we may want to use bootstrapping instead. So we want to bootstrap the regression. It always depends a little bit on what so the problems are, right? Robust regression is really something that we it's a method of choice if we feel that there are a lot of contaminated data points. All right. I hope that made it a little bit clearer. So what's the idea behind robust regression is. So there's these two examples. As I said, it can only stay on the surface. So we can only stay on the surface. We cannot go any deeper here because it's an introductory class. But yeah, okay. And I would say the rest of the time you can just talk about the next assignment again, or discuss anything else that you want to discuss. If there are like open questions or whatever, and let me know if you want to know anything or need clarification or some question is unclear, etc., etc. So I will stick around, and I would just open the breakout. No, what is it? Breakout groups again. Okay. 1 second. Alrighty. So based on what we have discussed today, are there any questions? Anything that's unclear?
Yeah, I'm not sure if I completely understood how the use of ANOVAs when compare. Well, this goes much earlier back. Using ANOVAs to compare models works.
Right.
In my mind. I don't think I entirely got that.
So what was unclear? I mean, was it in how to do it in R, or what's the idea is?
Oh, I think more the conceptual idea, because I understand like the syntax for it. I guess just more the concept in general.
It's very simple. So what you wanna do is, or what you wanna test is whether you have two models, right? So one model has 2 predictors, the other model has 4 predictors. And you find, okay, so my model that has 4 predictors has an R squared, or adjusted R squared of like 0.35. And my model that has 2 predictors has an adjusted R squared of 0.24. So, and what you want to know is this change in R squared from the 2 predictor model to the 4 predictor model, is that significantly different from 0? Or could that be something that just results, it's just a chance fluctuation, right? So you basically want to test, is that a significant increase in your prediction? Yeah, so whatever your difference is, in this case would be like 0.1 difference in R squareds. So you want to know, is your model that has more predictors, does it actually explain significantly more variance in your outcome variable?
Okay, that makes sense.
Yeah. So does adding the 2 predictors actually help? Or, right, it could be 5 more predictors, could be 1 more predictor. So right, it's just, there has to be at least one. Has to be at least one more. And that is the whole idea behind it. We have a restricted model that has fewer predictors, and a full model that has more predictors. And then you test whether the full model is doing significantly better in terms of explaining variance in the outcome variable, and that is quantified by the difference in R squared between the 2 models, than your restricted model.
Okay, and and also to add on to that, in the event that there's a non-significant result from that, would that indicate that there are variables outside of the ones being tested in the regression that are contributing to the variance?
Which one do you mean?
I just mean in general, like in an event that there's a non-significant finding, and say in the ANOVA between 2 regressions.
Oh, if you do the model comparison, and would be non-significant. Is that what you mean?
I mean, just in the case, like if you find a non-significant finding, or unless I'm just misunderstanding the concept again, if you find a non-significant finding between the two different models, would that just indicate that there's variance that something else is contributing to the variance outside of the ones being tested in both models?
No, it just means that the predictors that are in the full model are not doing anything. So it basically means that the second model is no better than the first one. First one might be a good model. I mean, of course, as long as the R squared is less than 100%, there are always other predictors that could improve the forecast or the prediction, right? So, but if you have a non-significant result for the model comparison using ANOVA, then it just means that the full model, so that the predictors that you included additionally in your full model don't really do anything to improve the prediction.
Okay.
So you can also drop them. You can just use your simple model. You don't have to. You don't need the right. If your two predictor model does just as well as the four predictor model, you don't need. So maybe I should mention that. So what you usually do, and I mean you don't have to, but it doesn't. In most cases, it's the only thing to make sense is that you have an overlap, right? So you have your full model includes the same predictors that you have on your restricted model. It's not from a theoretical, from a mathematical point of view, it's not required, but from an interpretational point of view, so it makes more sense in most cases, right? So if, like in our example, you have, so there's right? So you have the advertisement variable that explains so the number of albums sold, or predicts the number of albums sold, and then that is your restricted model, has only one predictor, then you're including two more predictors, but you still have the advertisement as one, right? You're not having three new. You don't compare the model that has advertisement as one predictor against a second model that has like attractiveness, numbers, so airplay and popularity, right, as predictors, and does not include advertisement. I mean, you could do it, but it will be a little bit harder to. In many cases, it will be a bit harder to interpret. Right, if you find difference between the two models or not, or if you don't find a difference, so what is it then? It's only right. So that's why you usually have an overlap. So you restrict your full model includes all the predictors that you also have in your complete model. And then if you don't find a significant difference, then you can just work with your reduced model, with your restricted model. So because the two additional predictors don't do much to improve, or do nothing to improve your prediction. Yeah, does it make more sense, or?
Yeah, I think that helps.
Okay. Yeah, so what you may want to do is then, if you get something like this, well, okay, so these two additional predictors are not very good. So maybe I should look for some other predictors to improve my prediction. So maybe, right, for our album sales example, I mean, in this case it worked. It's a sort of fictional data set, but I don't know. So like popular, so that's what I would, right? So general popularity of the band might be a good additional predictor. Or the, I don't know. Quality, it's hard to judge, right? The quality of the album.
Yeah, thank you though, that clears things up.
Okay. All right, any other questions? All right, so then I will open the breakout rooms. I will leave them open until 7, so you can stick around as long as you want. I will close them at 7, and just shoot me a message if some problems or questions come up. You can also just write it in the chat, right? Or you can meet me at 7.